Hello, everybody. Today we're going to shift gears away from machine level programming, although we will see some assembly in the future, so don't get too excited. And we're going to start looking at a different subject, specifically the memory hierarchy. So up until now, we sort of thought of memory as one big byte array that's accessed with an index known as an address. In reality, there's a pretty complex hierarchy of devices that provides that abstraction. And so we're going to sort of look at what memory hierarchy is and why it is the way it is. And then we're going to see these properties of these storage devices and properties of our programs and how these two things sort of come together in this nice way that leads to efficient programs. So we'll first sort of talk through some basic definitions with just to kind of get you familiar with the territory. Then we'll talk about this concept called locality, which is a property of our programs. And then we'll look at the memory hierarchy, understand specifically what a cache is, which is sort of one of the most important parts of the memory hierarchy in a computer. So first, let's just talk a little bit about some of the types of memory that exist in a computer. The sort of workhorse memory is what's called RAM, or random access memory. This is typically packaged in chips, and we may put multiple chips into our machines. Some of you may have done memory upgrades on your own machine at one point or another, perhaps, or at least maybe even seen a chip of RAM. Inside each of these sort of chips are these storage units called cells. And each of these cells stores on it an individual bit in on or off state. There are, in fact, sort of two varieties of RAM, SRAM and DRAM, static RAM and dynamic RAM. And it's, in fact, how the cells are implemented or sort of manufactured that differentiate these two types of RAM. So SRAM and DRAM are pretty different and different properties and ultimately different utilizations. So, the first thing to know is that SRAM is about 10 times faster than DRAM, so significantly faster. The other thing to note is that SRAM does not need a refresh, and so what this means is that sort of DRAM must be periodically sort of hit with a voltage and refreshed, and every bit of memory in that chip will be rewritten, and that happens every few milliseconds. If that fails to happen, then sort of the chip loses power and sort of the state of the chip is lost. Whereas SRAM will sort of stay set permanently and without error as long as it's powered. In terms of cost, SRAM is a lot more complex and is made of more expensive material, so it ends up being about 100 times more expensive. So this is a significant, sort of obviously a very significant difference in sort of cost and a contributing factor to why it's used the way that it is. SRAM is costlier, faster, more stable, so it ends up being used in these really fast, sort of smaller memories that are much closer to the CPU that are called cache memories. Whereas DRAM is typically used as like workhorse memory, so main memory, those chips that you might have replaced yourself in your machine or seen before. Those are likely DRAM, and those get used for sort of just everyday by all applications and most use cases. So SRAM and DRAM are what's known as volatile memory. This means that when they're powered off, they lose all of their information. So trying to think. So let's say you must have at some point maybe been working on a document in an unsaved state and had that program crash, and you've lost progress on that document, or you've lost data. This is an example of sort of data that was stored in a volatile memory, and once the power was lost, the data was lost. So obviously we know this can't be true of all storage. There's in fact another kind of memory known as a non-volatile memory that does retain its information even when it's powered off. We're not going to talk about it in too much detail, but probably worth mentioning just for completeness here. We won't dig into it too much in the course, but you should be aware there's a bunch of different kinds of non-volatile memory. They're sort of historically called read-only memories, although typically the newer ones can be reprogrammed to some degree. A ROM is usually something that has its sort of programming baked into it during its production. The operating system of your toaster, for example, might exist on some kind of ROM. If your toaster doesn't have a computer in it yet, it likely will someday. The most modern sort of form of these are EPROMs, or flash memories. And these you've probably seen many times, USB stick, for example. This is memory sort of that you can erase and rewrite in chunks called blocks. However, it will go bad after about 100,000 reprogrammings. This is actually what's in your phone, most likely. There are lots of uses, other than ones that I mentioned, for non-volatile memory. ROMs typically are the thing onto which firmware, and that's sort of what I was describing earlier with the toaster operating system. You may have the BIOS of your system, which is sort of the set of instructions to start up a computer that are sort of programmed onto a ROM. It kicks off the boot process and so forth, or other ROMs might be controllers for disks, network cards, so on and so forth. There's also, probably in your laptop right now is a pretty good chance, what's known as an SSD, or a solid-state disk. And these are sort of replacing the traditional rotating disks that older machines and desktops often, some still use. And they're in fact sort of orders of magnitude faster than the traditional sort of spinning drive disk. So now that we know what volatile RAM is, and we know what DRAM is, and so forth, we can look at RAM in the context of the system a little bit. Memories are connected to the CPU via wires collectively known as buses. Any operations that a CPU does that requires data be moved back to or from main memory will travel along these wires. What's on this slide here is a very high-level diagram that omits a significant amount of complexity and what actual systems really look like, but gives you an idea of how data flows through the system here. On the left, you can see we've got the sort of CPU chip itself, on which are a few different components. The first one you might notice is what's known as the register file, and this is the actual location where these registers like RAX and RDI exist. And next to it is the ALU, which is the thing that performs the operations. So it will read and write data to and from the register file as it's sort of doing operations. If an instruction needs to access memory, the bus interface is the thing that will handle doing that work. So let's say you're doing a move instruction of something from a register out into main memory, as we've done or seen before. Again, that's handled by the bus interface. So the bus interface would sort of move data along the system bus, which connects to something called the I/O bridge. It's called the chipset by Intel. It's just a subsystem that does some translation of the signal for the memory bus, which then ultimately the data arrives or is fetched from main memory. We'll not be studying the I/O bridge or the hardware level very deeply, but it's worth sort of having a loose understanding of. The key insight here is that these bus transactions are the transfer of data between main memory and CPU, and you might notice just how much farther away from the ALU main memory really is compared to the registers, something to sort of keep in mind. So as I mentioned, data can move back and forth between CPU and main memory. So suppose we want to do a load operation, aka a read transaction. So in other words, we're taking some data that resides in main memory and putting it into a register. So if you look at the move instruction on the slide here, it should look pretty familiar, and what it's saying is let's take the data that resides at address A and move it into register RAX. When the CPU is executing a move instruction like this, it first sort of takes that address of A and puts it on the bus interface, and it propagates itself down to the memory bus. At that point, main memory will sort of sense that that address is present, and it will then sort of read the 8 bytes at address A and place them back into the memory bus. And then finally, those bits sort of flow back over the IO bridge into the bus interface. The CPU senses that data is present and reads that data of X and puts it into the register. So that's a read transaction. Well, what about if we want to do a write transaction, or what might be called a store operation? Again, reading and writing is from the point of view of the CPU. So we're storing to memory from the CPU. We're sort of writing. So the CPU sort of starts this as it did in the read by placing address A on the bus. Main memory reads that address and then waits for the data to arrive on the bus. Next, sort of the CPU copies that data in RAX to the system bus. Finally, main memory reads that data from the memory bus and stores the bits in main memory. The point of all of this is that maybe to give you an intuition of just that main memory is, relatively speaking, very far away from the ALU. And a lot is going on when you read or write. Multiple operations, data traveling over the bus, all of this takes time. Whereas operations that occur with registers are comparatively very, very fast. Typically, memory operations take something on the order of 50 to 100 nanoseconds, whereas register operations are sub-nanoseconds. So we're talking 1 or 2 orders of magnitude difference when we go to main memory. And this idea of smaller, faster memories being closer to the ALU and so forth, and sort of the penalty of going further and further away is a recurring theme that we'll see as we continue to sort of study memories and memory hierarchies. Although I mentioned it briefly in the discussion of non-volatile storage, something we've not discussed in any detail is disk storage. So most of you probably know what a hard drive is. It's pretty different from the memory storage types that we've talked about in more detail. Disks traditionally are a pretty different physical nature and operate quite differently. We're not going to talk too much about that because for a multitude of reasons, not the least of which is that SSDs are similar to the RAMs that we have looked at and are increasingly common in replacing those traditional older style hard drives. For us at the moment, the only insight we need regarding disks is that in order to fetch and write data to them, it is orders of magnitude slower than going to main memory, which is in turn orders of magnitude slower than going to the register. So we should consider it to be a very costly operation. And so if you look at this graph here, the y-axis is the log scale of time in nanoseconds, orders of magnitude. The x-axis is years. And the lines sort of represent performance characteristics of some of the components that we've been talking about. And if we track these times and performance over the years, we see some interesting trends. So the first thing to note is that if you look at the CPU, every year cycle times were getting halved from 1985 up until about 2003. Components were being made smaller and smaller and closer together. Clock frequencies were increased. And then in 2003, CPU engineering hit that power wall that we discussed at the beginning of machine-level programming. So now, in 2003, we started getting sort of effectively more CPUs rather than faster ones. And this is a trend that's likely to continue in the future. But you can see that in 2003, the CPU cycle time sort of just levels off, right? It sort of stops. However, the effective CPU cycle time continues to decrease as we add more cores. So given that, we can sort of expect that we'll continue to see improvements or better effective CPU cycle times as more cores continue to be added. So let's look at some of these other performance characteristics. So SRAM looks like it's tracking CPU pretty well. Accessing SRAM is still orders of magnitude slower than a CPU instruction, but it's making progress. DRAM still has a pretty huge gap with the CPU. So access times have sort of not really gotten all that much better over the years. It's quite difficult to make it faster. And then, of course, disk, we're talking millisecond level response times. So it's a huge gap with everything else. About 40,000 times slower than SRAM and about 2,500 times slower than DRAM. So what's the point of all this? Well, our programs need data to work on. And if the CPU effectively keeps getting faster, but going to storage and access times don't get faster, then we have a problem. Because our computers can't run any faster because they can't fetch the data fast enough to actually make any use of the increased CPU speed. So to put it another way, our programs will be limited in performance by the time it takes to fetch the data. So this is called the CPU memory gap. And the reason that I mention it is because the memory hierarchy in combination with this basic fundamental program property known as locality is the key to sort of bridging this gap. And so now next we're sort of going to understand what locality is and then see how we can leverage it. So what is then this property called locality? Well, it's actually surprisingly intuitive. Most well-written programs actually tend to sort of exhibit this property already. And the idea is this. It's, as the definition states, programs tend to use data and instructions with addresses near or equal to those they have used recently. So in other words, if a program accesses a data item, the chances are very high that it will access that data item or one near it in the near future. So there's sort of two types of locality that we think about. Firstly, there's sort of temporal locality, which states that if you've referenced something recently, you're likely to reference it again. This sort of makes intuitive sense. I can give you a really common example. So imagine you had an array in which you were looping and summing the contents of that array. You would have some variable and a counter, and as you were performing that computation, you would be repeatedly referencing those same variables over and over again in a short amount of time. The second kind of locality is spatial locality, and that's the idea that items with nearby addresses tend to be referenced sort of close in time. So using our summing of an array again, if we were sort of going element by element through the array, then we're referencing items that are sort of have nearby addresses sort of right after each other, one after another. So in general, programs with good locality tend to perform better, and that's for reasons that we'll discuss in just a moment. When I talked about referenced items in the previous slide, we were likely thinking of data references or references to our variables. Turns out there is a second type of reference, though, that may exhibit locality, and that's the program itself, or the instruction references. So let's take a look at a small bit of code and see if we can understand it in terms of locality. So this code snippet here in the yellow box is hopefully simple to understand. It's just looping over an array called A and summing all of the elements into a variable called sum. We'll assume that each element of the array is an integer. So firstly, in terms of data references, a function like this that visits each element of an array sequentially is said to have stride 1 reference pattern. Well, that just means that we're sort of visiting each element in succession. So we're maximizing spatial locality here because we're accessing things with nearby addresses. It's worth noting that visiting every kth element of an array is called a stride k reference pattern, and generally speaking, as k increases, the spatial locality decreases. So we whenever possible, want to have that stride 1 reference pattern. And then in terms of temporal locality, we're referencing that sum variable each loop iteration. And remember, temporal locality is just this idea that recently referenced items are going to be referenced again in the near future. And that's clearly happening here with sum. So it seems like in terms of data references, this bit of code here has pretty good locality overall. Let's now think about it in terms of instruction references. I mean, keep in mind that since program instructions are stored in memory and have to be fetched by the CPU, we can sort of evaluate the locality of a program with respect to instruction fetches in the same way we would with references to data, or a similar manner. So in this case, for this particular program, we reference instructions in sequence in a loop. So the body of this for loop is one line of C code, but keep in mind that it would be multiple assembly instructions. So we're sort of referencing this sequence of instructions that are nearby, so we get good spatial locality. And we're looping over and over, and each loop iteration accesses the same instructions again and again. So that's going to give us good temporal locality. So sort of even in this very simple program, we can understand it in terms of locality, and we can see that we're actually doing pretty well here. So you may be wondering at this point what this has to do with memory hierarchies or the performance of your programs. Again, we'll get to that pretty soon, but in the meantime, you should just trust me that we as programmers should be able to look at a piece of code and have a good sense of its locality. Because as it turns out, programs with good locality run much, much better than equivalent programs with poor locality. So the question is, based on what we know so far, can we sort of identify good and poor locality? So let's evaluate this function. What does it do? Well, we have an array that is of 2 dimensions called A. We're looping through that array with a nested loop and taking each position and adding it to the sum. So one thing to sort of call to mind here is, what do we know about how 2-dimensional arrays are stored in memory when you write this code in C? Well, if you recall from the last lecture, it's done in what's called row major ordering, right? So all the elements of row 1 are stored followed by all the elements of row 2, followed by all the elements of row 3, and so on, contiguous in memory. So let's look at how we're looping. Well, you can see that we hold I sort of constant and then move through the columns, or j, by incrementing j. So if we were to look, sort of once we've completed all of the row i's elements, we then increment I to get to the next row and go through each column of that row by incrementing j. So if we looked at the addresses referenced by this loop in memory, it would be stride 1. Elements are accessed in that same row major order that they're stored in memory. So this has really good spatial locality and good temporal locality on the sum. So this is a good case. As it turns out, this same program could be written differently and be orders of magnitude slower. So what about this program? It's essentially the same program we saw on the last slide, but with the loops inverted. So you can see here that really the only difference is that we are now holding j constant in the outer loop and then looping on I in the inner loop. So how's the locality here? Well, given what we know about row major ordering, this is actually very bad. This is about the worst you can do, because we're holding j constant each time we loop and then jumping to each row. So we're sort of looping column-wise, and in the process, at each iteration, hopping from row to row per axis. This is a stride k axis where k is the size of the row. So this is very, very bad locality and should be avoided and would run very much slower than the same equivalent code on the previous slide. So here's one last example of locality, and I'll tell you in advance that it exhibits very poor locality. So the question is, can we change what indices the loops use so that this actually scans the array with a stride 1 reference pattern? So this code, really the difference between it and the previous slide is simply that we now have a 3-dimensional array. And you'll notice that we're using I as the counter in the outer loop, j as the counter in the second loop, and k as the counter in the most inner loop. Yet we hold k most constant, secondly j, and finally I. So we're hopping column-wise again through each of the arrays. If we wanted to modify this such that it would have stride 1 reference pattern, the solution would be to simply make this dimension k, leave j as is, and make this dimensions counter I. And then we would be doing a stride 1 reference pattern. Generally speaking, from going from right to left at each index, we should increment faster than its predecessor. So we want I to be incrementing faster than j, to be incrementing faster than k. And the way to do that again is to make k the counter here, j the counter here, and I the counter here. And then that would achieve a stride 1 pattern through this array. So that's the concept of locality. So now we can sort of reflect on what we've learned so far, and this will allow us to understand why memory hierarchies are designed the way that they are. We've observed so far that there are some properties of hardware and software that appear to be true. Is that fast storage technologies cost more, have less capacity, and require more power. And then we saw that there is that gap between the CPU and the axis at which we are accessing main memory and other locations on the system. And we've also noticed that well-written programs tend to have this quality of locality. So all of these properties in combination are what build us up to an approach for organizing memory and storage for optimal performance, and this is known as a memory hierarchy. So here is the idea, finally, of a memory hierarchy system. Instead of a flat memory system, you build a hierarchy of devices where the smaller, faster, more expensive storage devices live at the top. And then storage devices get slower, cheaper, and larger as we move from higher in the hierarchy to the lower levels. So you can see this example hierarchy here. At the very top, we have the CPU registers. And they are small in number, extremely expensive material-wise to produce, very, very close proximity to the ALU. And so a scarce resource, but the fastest, best performing resource. And then below that, on the hierarchy, you have your 3 tiers of the cache memories, which we'll cover what that means in a little bit soon. And these cache memories are SRAM based, and they can be accessed in a few CPU cycles. So a bit longer than, say, to access a register, which can be done in 1 CPU cycle, since 1 instruction can access a register. And these caches are megabytes in size, so they're getting a bit bigger than what the registers can hold. And then sort of below that is your main memory, or your DRAM, which can be accessed in tens to hundreds of cycles. And now we're talking about gigabytes worth of data that can be held within them. And so it sort of can typically holds data retrieved from the level down below it, which is the disks. These are slow but enormous, relatively speaking. Many hundreds of gigabytes, petabytes even. The old style disks are extremely slow. SSDs are better, but still orders of magnitude slower than the DRAM. And then sort of at the base of this hierarchy, you have disks on remote servers, perhaps. So maybe you have a cache of some data that you're storing somewhere else across a network. This is not an uncommon thing to do. If any of you have, say, Dropbox, for example, or Google Drive, you may store some files locally, but in fact they're hosted somewhere else on Dropbox or Google servers. So, but here is the key idea. Each level in the hierarchy holds data that is actually originating from the next level down. So the data that's in the registers is likely coming from the caches, and the data in the caches is likely coming from main memory. And the data in main memory is likely coming from the secondary storage, and so on and so forth. Before we move on from this slide, I just want to explain a bit of nomenclature very quickly. So we have these so-called L1, L2, and L3 caches that are sort of a new concept. They're a type of memory that sits sort of between main memory and the registers. So these are caches, which are special types of memory. But we also can say that for every level, that level acts as a cache for the level above it. So you might say that main memory caches data from local secondary storage. So to say it another way, as the definition states here, a cache is really a smaller, faster storage device that acts as a staging area for a subset of the data in the larger, slower device. So in that sense, registers are a cache for the L1 cache, and L1 cache is a cache for the L2 cache, and so forth. So to say it again, for each level k, the faster, smaller device at level k serves as a cache for the larger, slower device at level k plus 1. And so you might have already sort of come to this conclusion yourself, but that's where the idea of locality comes into play. Because of locality, programs tend to access the data at level k more often than they would access the data at level k plus 1. Therefore, the storage at k plus 1 can be slower and larger and cheaper. So to say that another way, locality states that if we reference something, it's likely that we're going to reference it again a number of times afterwards. So we can leverage that fact in our memory hierarchy. And if you read something once from slower memory, then you can store it in the next level up in the faster, smaller memory and read it many times. And so therefore, on average, you're reading more often from the faster, smaller memory than you are from the slower, larger memory. An analogy to help you get the intuition behind caches is the following. So let's say that you wanted to eat. You might have a few options. First, you could just go to the refrigerator, find something, and eat it. The latency is low. It's 1 minute. You can eat something very quickly. Alternatively, you could go out of your door and go to the deli. You go and buy something and then bring it home and eat it. Then, maybe takes 10 to 20 minutes depending upon how close your nearest deli is. And option 3 is to actually go out and grow the food. So you plant, wait for it to grow, and then finally eat it. So that latency is about 6 months. That's obviously far too long. So you can see how we can cache food at these different tiers along the way, which allows us to eat very quickly most of the time. Another analogy that might also help is to think of your backpack. Every morning when you wake up to go to school, you stick the stuff that you need into your backpack to bring to school, your computer, your notebook, whatever. If you had to go home every time you needed a pencil, obviously that would be extremely inefficient. But by having this cache on your back of the things that you need often, you can stay at school, and it's obviously much more effective use of your time. So let's take a look now at just caching and how it behaves in a somewhat general way. Next class, we'll take a closer look at how hardware caches will actually work. So you'll notice here that this diagram is emulating or demonstrating something that's something like an L-level cache sitting on top of main memory. So you'll notice that the storage in main memory is divided into these sort of chunks of data that are called blocks. And each block has a unique address or name, and they're typically of a fixed size in this scenario. You'll also notice that in the level above, in the cache, data is also partitioned into the same sized blocks, and that the cache contains a subset of the blocks that are in the main memory below it. And that data is copied between the two tiers in the hierarchy in these block size transfer units. So, if you have block 4 and it's going to be put into the cache, it's identified and slotted into one of the sort of slots available in the cache. Block 10 slotted into some particular slot in the cache. When a program needs a particular block or piece of data from a block from main memory, the memory system is going to first look in the cache to see if that piece of data is already loaded. So some data in some block is needed. Let's say it's block 14. We can see that we have that block present in our cache. This is what's known as a hit. This is great because it means that we don't need to take the extra time to go reach out into main memory to fetch block 14. Hit is good. This is the ideal case, and this is typically occurring because of locality. Some part of your program had recently already been using block 14, and therefore when it went to read at subsequent times, it was available on the cache. Alternatively, or sort of in contrast to a hit, is what's known as a miss, a cache miss. So that's the case where some piece of data is searched for in the cache by the memory system and it's not found. So say some block 12 is requested. You can see that here it's not present in the cache. So it needs to be, this is a miss, a cache miss, and so we're going to have to fetch that block from memory. So once it's fetched or found, we'll sort of take it and then we'll slot it into the cache somewhere, potentially overriding some other piece of, or some other block that we have loaded previously. Sort of placing that block into the cache and where it fits in which particular sort of location or slot is up to the placement policy, which we'll talk about more next time, and potentially determining which block gets evicted or removed from the cache is done in accordance to the replacement policy. That block that gets overwritten is sometimes known as the victim block. So there are, in fact, a few different reasons why you might have a cache miss. The first and sort of most edge case, I guess you could say, is the cold or compulsory miss. The reason why you have a cache miss is because there's nothing in there. Maybe the machine has just started up and nothing has been placed into cache yet. This is sort of what's known as your warming period as you load your cache. So as the cache warms, so to speak, you increase the likelihood of a hit. And this sort of occurs as programs execute. Once that cache is sort of warm and being utilized, we refer to the blocks that a program requires in cache to be sort of what's known as its working set. So the working set for some program is some set of data that fills the cache and stays resident in the cache for some period of time, making the program have much faster data access. So sometimes our program's working set could potentially be larger than the space we have available in the cache itself. This leads to what's known as a capacity miss. So when we have a set of active cache blocks that's larger than the cache itself. So let's say we have really good temporal locality for our program, but it requires 8 different blocks. And let's say we're using the cache system we saw in the last sort of diagram in the previous slides, where we only had 4 blocks available for the cache, 4 slots, so to speak. So we have a case here where our working set size is bigger than the cache capacity. And so we're constantly having, so that in this case we're sort of sometimes hitting but regularly missing as well, and those are capacity misses, because it's likely that the block you were looking for was recently cached but evicted in favor of some other block on the working set. And this can sort of happen over and over and over again in a cycle. We are constantly evicting things that you will shortly need thereafter, and then missing and then loading them again. This is what's known as cache thrashing. The final type of miss is what's known as a conflict miss. You see, there's some sort of algorithm that places the blocks in level K and from level K plus 1. So when we're taking a block, in other words, taking a block from main memory and sticking it in the cache, there's an algorithm that determines where to stick that block. It could be that the algorithm that calculates that proper slot in the cache could map the same different blocks to the same slot, right? So if you are this could be a case where if you have two blocks that both map to the same cache location, but are both in the working set, and you're sort of alternating between them, and you'll constantly be missing and loading that block, and then a few instructions later, missing and loading that second block that maps to the same slot. And this can continue ad infinitum, where you're sort of constantly overriding and missing and reloading the same block between these two blocks because they both map to the same slot in the cache. So I think that's roughly what we wanted to try to cover in this session. And next class we'll look more closely at real hardware caches and how they actually operate. And some of these general concepts that we've just been introduced to we'll understand in better detail. But in summary, what we sort of observed today is we've kind of seen a lot of things and discussed a variety of topics that have all convened on this idea of the memory hierarchy and caching. But we noticed that the speed gap between CPU and memory and storage continues to widen over time. And then we also noticed that well-written programs can have this property of good locality. And so we can sort of design memory systems and hierarchies based on caching and exploit that locality to actually mitigate the gap between CPU and storage access times. And that these caches are used really everywhere in modern systems, as we saw. So that's, I think, it for this session. I encourage you to read the book on these subjects. The coverage is succinct and good. If you have questions, please post them on Piazza or feel free to come to office hours.